Yesterday we looked at 4 new terms that we're somewhat unfamiliar with us. We've kind of heard of them before, but not real familiar with them because we haven't used them in a scientific way before. Those 4 terms were electric potential energy. And then we had electric potential energy difference. So these two sound almost exactly the same. Electric potential energy, electric potential energy difference. The third one was electric potential, which sounds an awful lot like the first definition again, except we're missing the word energy. That shouldn't make a big deal, right? Electric potential energy, electric potential, pretty much the same thing, right? Sounds like it at least. And then the fourth one we had was electric potential difference. So 4 terms, all of which sound an awful lot alike, but all 4 of which mean something slightly different from one another. Electric potential energy is given by the symbol E, and it's defined as it's defined as the energy stored in a system of 2 charges a certain distance apart. So you got a positive and a negative. There's a certain energy that's stored in that system of that positive and negative. Hey, something is going to cause the force that pulls the positive and negative together. That's the electric potential energy. Okay? A positive and a positive, they repel each other. Something has got to cause that force that pushes that positive and positive away from each other. That's the electric potential energy. Okay? It's analogous to gravitational potential energy. Now, electric potential energy difference, we're going to say that's delta E, right? Difference is delta, and E is energy. So electric potential energy difference, delta E, is the difference in potential energy. The difference in energy stored in a system of 2 charges a certain distance apart. So if I have 1 charge and the system has a certain amount, 2 charges, and the system has a certain amount of energy here, I move one of the charges, has a certain amount of energy here, the difference in the energy in that system from one place to the other is my potential energy difference. Now, what's another term that we sometimes use to describe electric potential energy difference? Work. So delta E is going to be equal to W. We also know that delta E or W is going to be equal to F times D, the force times the displacement. Electric potential. This is the one that seems to mess people up, potential. They get it mixed up with potential energy. Potential energy is the total energy that's stored in that system of 2 charges. Potential is the energy that's stored per charge, per coulomb of charge. So I think we used the analogy yesterday of money. If we had 30 people in the class, $120 total. The 120 would be analogous to the total energy. 4 would be analogous to the potential. Okay? It's the amount of money per person or the amount of energy per charge. The symbol for electric potential is V. The equation would be, well, if it's energy per charge, it would be E over Q. What would the units for that be? There's 2 sets of units that we can use. Both of them mean exactly the same thing. Joules per coulomb is one of them, and volts is the other one. This is kind of wacky that the symbol for potential is a capital V. The symbol for volts is a capital V. Okay, it's the same symbol for the variable as it is for the units there. Electric potential difference, well, it's the difference in energy per unit charge between 2 spots, or the difference in the energy stored in a system of 2 charges a certain distance apart per charge. So we're going to say that electric potential difference is delta V, and the easy equation for that is VF minus VI. The harder equation, the good news is that it's on our data sheet, is delta E over Q. The difference in energy per unit charge. The units would be what? Stephanie, what are the units for potential difference there? Good. Joules per coulomb or volts. It's just like work is in joules because change in energy is in joules. Okay. Delta V is in volts because V is in volts. That make sense? Now, we did define one more term as well, but this other term wasn't as closely related to the other ones as the 4 that you see up on the board right now are. The electron volt is a unit. Okay, it's not a quantity, it's a unit. Okay, it's not like saying energy, it's like saying joules, or it's not like saying speed, it's like saying meters per second. This is a unit. Okay, it's a unit of energy. It is the amount of energy that's gained or lost, depends on which way it goes, by an electron as it goes through a potential difference of 1 volt. The amount of energy that that's equal to in joules is 1.6 times 10 to the minus 19. So, you ever got to convert electron volts to joules? And you will have to do that quite a few times this year. We're going to set up a little ratio. 1 electron volt over 1.6 times 10 to the minus 19 joules equals, let's say we had 10 electron volts. 10 electron volts over x, solve for x. If, on the other hand, you were asked to convert joules to electron volts, let's say 3.2 times 10 to the minus 19 joules, we set it up the same way, except the x would go on the top here. 3.2 times 10 to the minus 19 joules is equal to x electron volts. Do the math. Take the 3.2 up, okay, divide by 1.6. All right, we had 2 questions for homework last night, page 566. I want to go over number 2 for sure. And if we need to go over number 1 as well, we will. Okay, but whether you think you need number 2 going over or not, we're going to do that one. Anybody for number 1? No? Okay, number 2 it is. It says the electron moves between 2 positions with a potential difference of 4 times 10 to the 4 volts. Tell me what that variable is. Potential difference. I hear that word potential. Okay, I'm starting to think, okay, that's going to be either E or V or delta E or delta V. Which one is it? Delta V, potential difference. It's not potential energy difference. Okay, it's not potential. It's potential difference. It's delta V. We're looking for the potential energy gained here. What are we looking for? It's not delta V. Is it V, E, or delta E? It's delta E, right? Okay, and we also have the charge and the mass of the electron as if we need them. I'm not going to write those values down in the question because I know I can check my data sheet to get them. Okay, but in the end here, I'm going to remind myself that I have those values just so that when I'm writing down my equation, I can kind of see what seems to fit better. Say delta V is equal to delta E over Q. We're rearranging this to solve for delta E. The Q goes up by multiplying. Looks like this. The electron has a charge of 1.6 times 10 to the minus 19 coulombs, and the potential difference is 4.00 times 10 to the 4 volts. And multiply those together, we get 6.40 times 10 to the negative 15 joules. Okay, we know that's joules because we use standard units in our equation, coulombs and volts. Well, then we're going to get standard units out of it, joules, not something like electron volts or kilowatt hours. But now we do have to convert to electron volts. So let's say 1 electron volt over 1.6 times 10 to the minus 19 joules, and that's the conversion factor on my data sheet, equals x electron volts over 6.4 times 10 to the negative 15 joules. Solve for x. We get 4.00 times 10 to the 4 electron volts. The same number as we had for potential difference. Is that a coincidence? Yes and no. Okay, if you answered yes, you're right. If you answered no, you're right. Or wrong in both cases. I don't know. There's some aspect of coincidence to it, but it's not a complete coincidence here. Okay. Will it always be the same? Will the electron volts always be the same as the potential difference? Okay? No, they won't. They will be in this case, but they won't always be. It's the same in this case because we're using an electron, and that's how we define an electron volt. The energy gained or lost by an electron as it goes through a potential difference of a volt. Okay, if we used an alpha particle here or something with a charge other than that of an electron, then this number wouldn't have been the same as the potential difference. Does that make sense? Here's my recommendation. Don't remember that delta V and the energy in electron volts are the same for an electron. Okay, don't remember that. It always will be the same, but don't remember that. Okay, figure it out. And then once you figure it out, you say, oh yeah, Wait a second, they're the same number. Does that make sense? Yeah, it does, because we're using an electron here. You kind of think about that after the fact. The danger of remembering that this is going to be the same number as this is that sometime when it's not the same, you're going to forget and just make it the same. Okay, so figure it out each time and then kind of look back at it and say, oh yeah, it should have been the same. All right? Got a few multiple choice questions for you to look at here. The first one, multiple choice number 60. I'd like you to submit that, please, as multiple choice number 1 for me. All right, guys, we've got almost all of you having responded now. I got exactly the results that I thought I would get on this question. Most people, 83% of you got the correct answer, 17% of you got the incorrect answer, but all 17% that got the wrong answer picked the same thing. And I'm not surprised at which one you picked. The answer is B. Everybody who got the wrong answer picked D. Now, why'd you do that? Well, we want to find the energy gained by a proton when it moves through a potential difference of a volt. Delta V is equal to delta E over Q. So we're going to rearrange that equation. Delta E is equal to Q times V. Right? Q times delta V instead of Q times E. Q times E is force. Right? It comes from the electric field. Q times delta V is energy. So don't get those two mixed up. Multiply the charge of the proton 1.6 times 10 to the minus 19 by the potential difference of 1.0 volt. And what do I get? Well, lo and behold, it's 1.6 times 10 to the minus 19. But what are the units that we have there? Joules, right? If we're using joules, volts and coulombs, then we're going to get standard units out of this as well, 1.6 times 10 to the minus 19 joules. Now, that's not an option. Since that's not an option, I better convert to another set of units that I see there. 1 electron volt over 1.6 times 10 to the minus 19 joules equals X electron volts over 1.6 times 10 to the minus 19 joules. Well, it doesn't take a genius to figure out what X is there. It's 1. So 1 electron volt is my answer there. Does that make sense? Okay, the 17% of you got this question wrong. That's okay. You were on the right track. You just didn't go far enough. Okay, you stopped with units. Okay, you got stuck on joules and just said, oh, the number that I got is there. It must be the answer. Pay attention to those units. Okay, pay attention to those units. Okay, let's take a look at multiple choice number 61 now, please. Actually, you can do 61 and 62 together. 61 and 62 together. So 61 will be multiple choice number 1. 62 will be multiple choice number 2. Let's have a look here, everyone. Question number 61 says, when the neutral pith ball is placed near the Van de Graaff generator, charged Van de Graaff generator, the pith ball is attracted to the generator as a result of what? Well, the Van de Graaff generator is going to be negatively charged. This is going to be neutral. It's attracted, right? We know that neutral is attracted to negative. Why is it attracted to negative? Because of a separation of charge, right? The charge in the pith ball, the positives stay where they are, but the negatives are going to get pushed away as far away as they can. That leaves us with a charge separation. Positive side here, negative side here. Positive is attracted to negative. So the entire neutral pith ball will be attracted to the negative dome. That's induction, right? There's no charge being transferred there. That's going to be induction. So that's going to be A. 95% of you said that one. The next question, 100% of you got the right answer, or the wrong answer, hopefully the right answer. The direction of the electrical force on the pith ball is which way? Well, if this pith ball is being pulled toward the Van de Graaff generator, the force on the pith ball must be this way. Now, the force on the generator is the other way, but that's not the question, right? We're trying to find the force on the pith ball. So it's going to be to the left, which is exactly what all of you said. Here's the tough one. Let's see what you can do with 63. Okay, submit this as multiple choice number 1, please. The electric force on the pith ball by the generator. So we want to find the value of that electric force. Okay, let's see what you can do on that one. Okay, let's have a look here now, guys. I remember when this question first appeared on a diploma exam, it was 10 or 12 years ago when it first appeared. Since that time, we've had 3 or 4 times when there's been a question that's been somewhat like this. But that's the first one that I ever remember seeing. And I remember seeing it for the first time thinking, holy cow, like this is insane. This is stupid. Not stupid as in it's a terrible question, but stupid as in this is really, really hard. Okay. And honestly, at first, I didn't know what to do with it. Okay, my first instinct is probably the same as your first instinct, and that is to say, look, we're looking for the electric force. Let's use the equation for electric force. KQ1 Q2 over R squared. I got a problem with that, though. Okay, I know what R is, I know what K is. I don't know what either of the charges are. Actually, that's not true. I know what the pith ball is. It's 0. But I don't know what Q2 is. I don't know what the Van de Graaff generator ball is. This only works when you have charges anyways. That equation doesn't work if you have two neutral or a neutral object. Okay, you've got to have two charges. So that's not going to work if you have a neutral pith ball. It's just not going to work. So then I thought, well, what else gives me electric force? The only thing I could think of was my electric field equation for an experiencer, E is equal to F over Q. Rearrange that equation, we get F is equal to Q times E. Sounds good until I realize that I don't know what the charge is, and I don't know what the electric field is. So, okay, 0, yeah, you're right at the pith ball, yeah. But I don't know what the electric field is, so what am I going to do then? At this point, I'm at a little bit of a loss. And that happens every once in a while, okay? Even though, I've been through this so many times, and I know this stuff, I think, pretty well. Every once in a while, I still get a question that's just like, what do I do? What do I do with this? But here's the difference between you and I, between many of you, I should say, and I. Okay? I'm not afraid to try something. Okay? I'm not afraid to take a risk at solving a question. If I don't know what to do with this question, that's okay, because I'm confident I'll be able to get it. Okay? I just have to try something. Now, I'm not going to try random things. Like, I'm not going to say all of a sudden, oh, wait, maybe that'll work. No, I'm not going to try that because I know that's not valid, right? But I will try things that are correct. For instance, when I saw this, after I tried F is equal to KQ1 Q2 over R squared and then the electric field equation, not sure what to do, so I thought, well, I got forces. I got a force downward on this pith ball. It's the force of gravity. Okay, it's equal to the mass times 9.81, 2.5 times 10 to the negative 4 times 9.81. What does that give me, by the way? 2.4525 times 10 to the minus 3 newtons. All right, look, that's something. Okay, some of you may look at that and say, it's force of gravity. It's not what I'm looking for. I don't care. Okay, that's a step ahead of where most of you were. Okay, most of you didn't know what the answer for electric force was. Okay, I don't have electric force right now, but at least I've got something that you didn't have. Okay, so there's a step forward. Now, in the end, that may not lead me to the correct answer. It may not lead me to an answer, period, but it's worth a try because it's valid, it's correct. It's not like saying V equals D over T for an object that's sitting there. Okay, it's a correct answer for the force of gravity. It's just not what I'm looking for. Well, look, I also have an attractive force, an electric force here that's pulling to the left, right? And I also have a string that's pulling up this way. We'll call it Ft for the force of tension. And that's when it struck me. Okay, the first time I did this question, that's when it struck me. When I was drawing this diagram, I didn't know where I was going with it. Honest truth. I didn't know where I was going with this diagram. I didn't know if it was going to help me or not. But I did it because it was the only thing that I could think of that was valid. So I did it. And then at some point, something struck me. Thought, wait a second, if this pith ball is at rest, if this pith ball isn't moving, then forces have to balance. In other words, if there's a downward force of 2.45, then there has to be an upward force of 2.45. The upward force of 2.45 is the y component of tension. And then, well, look, if it's not moving left or right, and there's a force to the left, then there must also be a force to the right, the x component of tension. And that force to the right, it's got to be equal to the electric force. So now it's easy if you recognize some trigonometry here. Look, I've got the angle. I'm going to say tan 20 degrees is equal to the opposite side. Okay, I'm going to call it x actually. The opposite side is x. The adjacent side is 2.4525 times 10 to the negative 3. We solve for x there, and I think it works out to be 8.9 times 10 to the minus 4. Now, what have we solved for there? Directly, we've solved for the x component of the tension in the string. Indirectly, because I know the x component of the tension of the string has to be the same as the electric force, indirectly I've solved for the electric force. So the answer for that question would be C. Does that make sense? Listen, guys, 45% of you guys? Oh, sorry, 39% of you guys. 39% of you guys actually got this question right. I would bet that that's about twice as many as provincially on a diploma exam would get this question right, having seen it for the first time. Okay, that's actually, doesn't sound very good, like only 40% of you got it right, but it actually is pretty good for a question like this, okay? If 40% of you got a question like this correct the first time you ever saw it, I would be happy with that, believe it or not. Having said that, I wouldn't be happy now if you saw a question like that with 40% of you, because you know where to go with this now, right? You don't have to think so much on your own. Okay, you know where to go with it. Draw your free body diagram. You know that the forces have to balance. And the first time this appeared, it was a brutal question. It's appeared 3 or 4 times since that. People still didn't perform all that well on it, but they should have. Okay, once we've seen it, it should have been done a lot better than the first time when we hadn't seen it before. Okay? You guys feel okay about that? Don't quote me on this, but I think at some point this year, I think it's on your unit test on Tuesday, actually, I think. But at some point this year, I've put a question on a test that's similar to this. Not the same, but similar to this, where you have to use the same logic. And I think it's on Tuesday's test. All right?